Welcome to Science Talk, where we journey through the enigmatic concepts shaping our universe. In this episode, we explore the intersection of chaos and order through stochastic processes, entropy, and complex systems. These principles are far from abstract, they underpin everything from the evolutionary dynamics of galaxies to the delicate flight of a butterfly. Stochastic processes, the essence of unpredictability. Stochastic processes reveal the inherent uncertainty in phenomena around us. From the whimsical descent of a leaf to the fluctuating heartbeat of the stock market, these mathematical models help us understand the unpredictable nature of the world. Stochastic processes are fundamental in modeling and understanding the unpredictable dynamics in various phenomena. Here's a brief overview highlighting their importance. Nature of stochastic processes. Stochastic processes are mathematical models that represent systems or phenomena that evolve over time in a way that is inherently uncertain. They are used to describe and predict the behavior of complex systems where the exact outcome is uncertain but follows certain statistical properties or patterns. Applications across fields. Finance. In the stock market, stochastic processes model the random movement of asset prices, interest rates, and market risks. Physics. They are used to model random physical processes such as particle diffusion. Biology. In population dynamics, they model the growth and decline of populations under random environmental impacts. Engineering. Stochastic models help in assessing reliability and failure rates of systems under uncertain conditions. Key models and their use. Brownian motion represents the random movement of particles suspended in a fluid, a foundational model in finance for option pricing. Markov chains, used for systems that transition from one state to another, where the future state depends only on the current state and not on the sequence of events that preceded it. Poisson processes model the occurrence of events over time, used in queue theory, telecommunications, and traffic flow analysis. Mathematical representation. A stochastic process is defined as a collection of random variables indexed by time. Each random variable describes the state of the process at time. Understanding uncertainty. By quantifying uncertainty, stochastic processes allow for the development of strategies for prediction, optimization, and control in uncertain environments. They provide insights into the variability and predictability of systems. Challenges in research. Parameter estimation, estimating the parameters that govern the stochastic process from observed data. Model selection, choosing the correct model to accurately describe the observed phenomena. Predictive analytics, developing methods to predict future behavior of the stochastic process. Entropy, the narrative of disorder. Entropy measures disorder in transformation, illustrating the inevitable progression towards chaos. This concept bridges diverse fields, from the decay of celestial bodies to the evolution of digital communication, highlighting the transformative nature of information and energy. Entropy is a multifaceted concept that serves as a cornerstone in various scientific and mathematical fields, encapsulating the principles of disorder, uncertainty, and transformation. Below is a concise examination of its significance. Thermodynamics and physics. In thermodynamics, entropy quantifies the degree of disorder or randomness in a system. The second law of thermodynamics posits that the total entropy of an isolated system can never decrease over time, implying that systems naturally progress towards a state of maximum disorder. This concept is crucial in understanding energy distribution, the efficiency of engines, and the irreversible nature of physical processes. Information theory. Introduced by Claude Shannon, entropy in information theory measures the uncertainty or unpredictability of information content. It is a measure of the average information content one is missing when one does not know the value of the random variable. This form of entropy is foundational in digital communication and cryptography, guiding the design of efficient coding schemes and secure communication protocols. Quantitative measure. In a closed system, entropy is quantitatively defined with the Boltzmann constant, the number of microstates consistent with the macroscopic state. In information theory, the entropy of a discrete random variable is defined as the probability of occurrence of the state. Biological and ecological systems. Entropy applies to the evolution and complexity of biological systems, reflecting on the disorder within ecosystems and the flow of energy through food chains. It provides insights into the organization, resilience, and dynamics of living systems, illustrating the balance between order and chaos. Societal and economic systems. Concepts of entropy have been applied metaphorically to understand social order, economic systems, and the spread of information or misinformation within societies. It illustrates the flow of information in social networks and the transformation of economic systems over time. Technological and computational complexity. In computer science, entropy is a measure of the unpredictability or complexity of a data set, influencing algorithms, data compression, and the security of cryptographic systems. It plays a role in optimizing algorithms and understanding the theoretical limits of computation and communication. Entropy, in its essence, encapsulates the inevitable progression towards disorder, serving as a bridge across disciplines by providing a fundamental understanding of transformation, information, and energy. Its study illuminates the underlying principles guiding the evolution of complex systems, from the microscopic realm of particles to the macroscopic dynamics of the universe. Applying theory to practice, financial markets and beyond. In the financial world, Monte Carlo simulations utilize stochastic processes to predict market trends and assess risks, offering a strategic advantage in navigating economic uncertainties. Monte Carlo simulations represent a pivotal technique in the financial sector, leveraging stochastic processes to forecast market trends and evaluate risks. This method involves generating numerous simulations to model the probability of different outcomes under uncertainty. Here's a detailed look at how Monte Carlo simulations are employed within finance. Understanding Monte Carlo simulations. These simulations use random sampling and statistical modeling to estimate mathematical functions and mimic the operations of complex systems. The core idea is to generate a large number of potential future outcomes for a random variable or variables affecting financial decisions, based on their probability distributions. Applications in finance. Portfolio risk and return analysis. They are used to predict the likely performance of investment portfolios, assessing the probability of achieving specific financial goals and understanding the risks involved. Option pricing. Monte Carlo simulations model various future paths of underlying asset prices to calculate the value of options and derivatives, taking into account the volatility and other market factors. Value at risk. VAR. This method estimates the maximum potential loss in a portfolio with a given confidence interval over a specific period, helping in risk management and regulatory compliance. Asset allocation. By simulating different market conditions, investors can analyze the potential impacts on their assets, aiding in strategic allocation and diversification to optimize returns. Methodology. Define the market model or financial metric to be analyzed. Determine the probability distributions of the key input variables, which could include interest rates, market returns, or asset prices, based on historical data or market assumptions. Run numerous simulations, each generating a potential future outcome based on random sampling from the input distributions. Aggregate the outcomes to form probability distributions for the metric being analyzed, providing insights into expected returns, potential risks, and the likelihood of different scenarios. Advantages. Flexibility. Can model complex financial instruments and market scenarios that are analytically intractable. Risk assessment. Offers a detailed view of potential risks and returns, enabling better decision-making under uncertainty. Strategic planning. Helps in stress testing strategies under various market conditions, supporting robust financial planning. Challenges. Computational intensity. Requires significant computational resources, especially for complex models or a large number of simulations. Model risk. The accuracy of the results depends heavily on the chosen model and the assumptions regarding probability distributions and market dynamics. Data sensitivity. Outcomes can be highly sensitive to the input data and distribution assumptions, necessitating careful validation and sensitivity analysis. Challenges in turbulence study. Complexity. turbulence is inherently complex and difficult to model accurately due to its chaotic nature and sensitivity to initial conditions. Computational demands. High-fidelity simulations of turbulent flows require substantial computational resources, making it challenging to model large or complex systems in detail. Theoretical understanding. Despite advances, a complete theoretical understanding of turbulence remains elusive, with ongoing research seeking to unravel its underlying principles. Research and innovation. Direct numerical simulation, DNS. Although computationally intensive, DNS resolves all scales of turbulence and provides detailed insights into the mechanics of fluid motion. Large eddy simulation, LES, and Reynolds averaged Navier-Stokes, RANS, models. These are more computationally efficient approaches that model larger eddies directly while approximating the effects of smaller scales, used widely in engineering applications. Experimental studies. Advances in visualization techniques and measurement technologies, such as particle image velocimetry, PIV, enhance our ability to observe and analyze turbulent flows directly. The study of turbulence through fluid dynamics and the Navier-Stokes equations is not only a pursuit of fundamental scientific understanding but also a critical endeavor with practical implications across many sectors. By decoding the structured chaos within fluid flows, scientists and engineers can improve predictions, enhance designs, and solve complex problems in various fields, from environmental management to the advancement of technology in aerospace and beyond. Complex systems and quantum uncertainty. The Ising model and quantum principles like the Heisenberg uncertainty principle demonstrate the intricate balance of determinism and randomness in the universe, challenging our understanding of reality. The Ising model and quantum principles such as the Heisenberg uncertainty principle play pivotal roles in unveiling the complex interplay between determinism and randomness within the universe. These concepts not only challenge our foundational understanding of reality but also provide insights into the behaviors of systems at both macroscopic and microscopic levels. Here's how they contribute to our understanding. Ising model. Overview. The Ising model is a mathematical model of ferromagnetism in statistical mechanics. It consists of discrete variables that represent magnetic dipole moments of atomic spins, which can be in one of two states, +1 or -1. The spins are arranged on a lattice, and the model evaluates how the spins interact with each other in an external magnetic field. Determinism and randomness. The model demonstrates how simple rules at the microscopic level can lead to emergent behaviors and phase transitions at the macroscopic level. It shows that under certain conditions, an ordered phase, where all spins align, can spontaneously arise out of disorder, illustrating the balance between randomness, thermal fluctuations, and determinism, spin interactions. Applications. Beyond physics, the Ising model has been applied to various fields such as neuroscience, social dynamics, and economics to model systems with binary states and interactions. Quantum principles. Heisenberg uncertainty principle. Overview. The Heisenberg uncertainty principle is a fundamental theory in quantum mechanics stating that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. The more precisely one property is measured, the less precisely the other can be controlled or known. Determinism and randomness. This principle challenges classical determinism, introducing inherent randomness into the very fabric of reality. It implies that at the quantum level, the universe is governed by probabilities rather than deterministic laws. Impact on reality. The principle has profound implications for our understanding of the universe, suggesting that at a fundamental level, nature is governed by chance, affecting fields ranging from quantum computing to philosophical interpretations of reality. Bridging the gap. Both the Ising model and the Heisenberg uncertainty principle highlight the nuanced relationship between determinism and randomness. They suggest that while macroscopic phenomena can often be predicted with a high degree of accuracy using classical physics, underlying these phenomena is a quantum realm dominated by probabilistic behavior. This duality is at the heart of modern physics and continues to be a source of investigation and fascination in attempts to unify classical and quantum theories. Concluding thoughts. The dance of chaos and order. Our exploration underscores the interplay of stochastic processes, entropy, and complex systems in understanding the universe. These concepts remind us that chaos and order coexist, shaping the cosmos and our comprehension of existence. The exploration of these models and principles deepens our understanding of the universe, offering insights into the fundamental nature of matter and energy. They remind us that beneath apparent chaos can lie structured patterns, and that at the quantum level, uncertainty is not a deficiency in our measurements but a fundamental property of nature. This interplay between determinism and randomness is a key aspect of the ongoing quest to grasp the complexities of the universe.